Hello everyone, my name is Jong John and I'm a researcher at the IBS CMFD in Seoul, Korea. Here I will briefly introduce my recent work on the lithium-ion transport in concentrated aqueous electrolytes that can be used in lithium-ion rechargeable batteries. This study is based on molecular dynamics simulations and theoretical analysis. In this work, I studied an electrolyte solution called WISE, that is water in salt electrolytes, and it's a concentrated aqueous solutions of lithium electrolytes with comparable concentrations of water and lithium ions, and it's safer than organic solvents used in conventional lithium-ion batteries, and also it has a good electrochemical performance. It was proposed by Wang Xu and co-workers in 2015. They used this lithium TFSI salt dissolved in water with a saturation concentration of 21 molality. So there are two requirements for the success of WISE. One is the high salt concentration for favorable electrode chemistry. Another is the fast lithium-ion transport for high ion conductivity. Here, we are looking at the ion conductivity as a function of salt concentration for one WISE made of lithium TFSI and two organic electrolytes based on propylene carbonate. We can see that the conductivity of WISE at 5 mole concentration is comparable to that of organic electrolytes at much lower concentration, and it cannot be explained by the macroscopic viscosity of the solution. So the question is, why is the conductivity of WISE much higher and much less hindered by viscosity than organic electrolytes? To answer this question, we considered pairwise atomic interactions in aqueous solutions of lithium TFSI. We identified only 4 kinds of specific intermolecular interactions involving 2 atoms of water molecules and lithium ion and the sulfonyl oxidants of TFSI and ions. Here are those 4 interactions. And we developed a computational model of lithium TFSI and performed MD simulations from 1 to 21 molality concentrations and analyzed the radial distribution functions and the contact numbers, which is given by the integration of the radial distribution function. From this analysis, we found that lithium ions interact more strongly with water oxidants than with TFSI oxidants at all concentrations, but the gap narrows at higher concentration. Also, we can quantitatively determine the strength of atomic contact pairs, which shows that the lithium water-oxygen interaction is the most stable at all concentrations, and hydrogen bond network weakens with concentration. Also, lithium ion is coordinated by 4 oxygens either from water or TFSI, and the fraction of OT increases with concentration. We also studied the dynamics of atom pair interactions using the reactive flux time correlation function approach developed by Ruja and Chandler and the transition state theory. These methods reflect different aspects of the molecular interaction and dynamics. Using the reactive flux time correlation function method, we obtained the lifetimes of 4 types of atom pairs, which increase by an order of magnitude from 1 to 21 mole. And the transition state theory lifetime is much shorter by 1 to 2 orders of magnitude, as this plot shows. However, the order of lifetimes is the same whether we use reactive flux TCF or TFT. And we find that the lithium OW has the longest lifetime at all concentrations. Therefore, this lithium OW is the most stable both thermodynamically and kinetically, and regardless of the solvent dynamical effects. However, the gap between lithium OW and lithium OT is the smallest at 21 mole concentration. We have also investigated the correlation of lithium-ion transport and the local solvation structure and dynamics. First, we determined the lithium-ion displacement delta R, like this, using the short time span. And we calculated the atomic composition of the first solvation shells of lithium ions. That is the average number of OW and OT in each solvation shell over a short time span. And to study the dynamics of lithium-ion solvation, we calculated the number of holdover atoms, MOW or MOT, that is the atoms found in each solvation shell at the beginning and end of a short time span. Now we summarize the result of this study. We find that the lithium-ion trajectory is heterogeneous, with distinguishable water-rich and anion-rich fragments. So in this figure, the lithium-ion moves from 0 to 1 nanosecond, and the empty regions correspond to this water-rich fragment, and this green region is the anion-rich fragment. And also, a lithium-ion always accompanies 1 to 4 water-oxygen atoms, and if there are more water-oxygen and pure TFFI oxygen in the lithium-ion solvation shell, then that lithium-ion will move faster. And also, if more lithium-OT pairs are broken in a given time span, that lithium-ion will have a larger displacement in that time span. So combining all these, we can conclude that the subtle balance of lithium-OW and lithium-OT interactions that enables this easy exchange of these two in the lithium-ion solvation shell, and it leads to faster lithium movement. For further details, please see this paper published this year, and I'd like to thank you for your attention.